Hey everybody, today we are starting chapter 4, atom bonds, and we are going to start out by talking about ions and ionic compounds. Now this entire slide deck that you have available to you on Canvas is the entirety of chapter 4, where we're going to talk about ionic, molecular compounds, as well as molecular structures. So as you can see, we have a number of different learning objectives in this chapter. This video, however, is going to be focusing primarily on the first 4 learning outcomes, where we are going to learn how to write the symbols for simple ions, how to use the charge balance to write the correct formula for an ionic compound. Given the formula for an ionic compound, write the correct name, and when given the name of an ionic formula, write the correct formula, as well as write the name and formula for ionic compounds containing polyatomic ions. When we come back for part 2 of this lecture, we will learn how to work with molecular compounds. And then in the third part of the lecture series, we'll talk about electronegativity and bond polarity, as well as predicting three-dimensional structure and the intermolecular forces that exist between molecules. All right, so let's go ahead and start focusing on the first unit in this chapter, which is all focused on ions and ionic compounds. So this chapter is probably going to take us about a couple weeks to navigate, so please don't wait till the last minute to do the homework, because there will be a little bit more homework questions than normal. You will have 2 weeks to do the homework, but you want to make sure you go ahead and start knocking it out now, right? So do a little bit each day as we cover new material, so that you can help reinforce the discussions that we have in class. And then for lab, we're going to build solar batteries in order to help us learn the importance of ionic compounds and converting solar energy into electrical energy. Okay, so let's talk about what is a molecule first. So a molecule is simply a group of 2 or more atoms held together by chemical bonds. A molecule may consist of 2 atoms of the same element or many atoms of many different elements. Now, as we begin to understand and study molecules, we are also very interested in the shape that these molecules take. The shape of the molecule is going to be driven by the different atoms and elements that exist in the molecule, their sizes, their electronegativities, how many valence electrons do they have. All of this is going to help influence shape. And then once we understand the shape of the molecule, the shape is going to help us understand the physical and chemical properties of the molecule. Using shape, we can predict how molecules will interact with other molecules, how molecules react with each other, the boiling points and freezing points of molecules, as well as their relative solubility in different solvents. So why do atoms bond? Well, one of the driving forces between creating bonds is something chemists call the octet rule. And we can define the octet rule as the tendency of atoms to attain a stable electron configuration between atoms by either sharing, losing, or gaining electrons in order to obtain an octet of 8 electrons in the valence shell. This can occur through either ionic or covalent bonding. So when we have ionic bonding, electrons are transferred from one atom to another, and the 2 atoms associate through opposite charges, whereas in covalent bonding, electrons are shared equally between the atoms of the molecule, and you aren't transferring them, they are shared between the 2. So those electrons are seen by both atoms. So again, just to reiterate, ionic bonds occur when valence electrons of a metal atom are transferred to the atom of a nonmetal, right? So here we have our metal atom. The metal gives up its electron to the nonmetal. We end up with a positive charge on the metal, a negative charge on the nonmetal, and we have association between the two atoms because of the opposite charges. Covalent bonds, however, occur when two or more nonmetal atoms share electrons. So as we can see, we have two nonmetals. There's two electrons between them that end up being shared or felt by the nuclei of both atoms. So here the association between the atoms is the equal sharing or relatively equal sharing. Sometimes it's not equal. We'll talk about that. But at the same time, these electrons are existing between the two nuclei, whereas in the ionic bond, the electrons are solely on the nonmetal and not on the metal. So let's talk about ions. So first, what is the difference between an atom and an ion? We already know this, but let's review. Atoms are electrically neutral, which means we have the same number of protons and electrons. And the number of protons, remember, defines its element. So remember, the atomic number is the same as our number of protons. If we are electrically neutral, then the number of electrons will also be the same as the atomic number. Ions, however, are electrically charged. So we have a different number of protons and electrons, and this may contain one or more atoms, right? We could have different charge states sometimes for the ions. We can have positive, we can have negative, and we can have different ratios of protons to electrons in any given ion. Now, atoms have a tendency to form a certain ion, and again, this is going to be due to the octet rule, or the desire for metals to have 8 electrons. So when we're looking at the periodic table, we can see that cations or positive ions are going to be formed mostly by metals, and specifically metals in group 1A, 2A, and 3A. So 1A, 2A, and the 3A metals, not the nonmetals, but the 3A metals are all going to likely form positive cations, meaning they're going to lose electrons. And this is because, if you recall, when we were talking about periodic trends, they have very low ionization energies, meaning they can readily lose one or more of their valence electrons to form the cation, or the positive charged ion. They typically are going to lose electrons until they have the same number of valence electrons as their nearest noble gas to satisfy their octet. So for example, if we are talking about calcium, calcium has 20 electrons, but if you do the electron configuration, you will see that there's only 2 electrons in its outermost energy shell. So it has 2 valence electrons. Remember, we can look at our group number. Our group number is 2A, meaning we have 2 electrons in calcium. Now calcium, again, every atom wants to have an octet. So calcium would rather give up 2 electrons to become like argon with 18 electrons, or 8 electrons in its valence shell, than it is to pick up 1, 2, 3, 4, 5, 6 electrons to become krypton. So remember, we have very low ionization energy. We don't really care to pick up electrons. We would rather just give them up to drop down into the 3p's versus building up into the 4p orbitals to satisfy the octet. So calcium, if it loses 2 electrons to become like its nearest noble gas, then we are going to become a calcium 2+ cation. When we name these elements, or when we name these ions, if it's the cation, it's named by the element name. So if we have a cation of calcium, it is just named calcium. So again, we can visualize what's happening here by looking at sodium. If we go back to the periodic table, we see that sodium is a group 1A element. It has one valence electron in the 3s orbital. So if we look back, here is our 3s orbital, or our third energy shell, in which sodium has one valence electron. Again, atoms have two choices. They can either pick up enough electrons to satisfy their octet in the current energy shell that their valence electrons are in, or they can lose electrons to drop down into the next energy shell. So for sodium, it's going to be much easier to lose this electron and drop down to the 2 energy shell versus picking up 7 more electrons to fill the 3rd energy shell. So when this happens, sodium is going to lose an electron, dropping down from the 3rd energy shell to the 2nd energy shell as their valence shell, and will be written as sodium 1+ and named as sodium, or the sodium ion. Same thing with magnesium. Again, magnesium is a group 2A element with valence electrons in the 3rd energy shell. Here we have 2 electrons. Again, it's going to be easier for magnesium to lose these 2 electrons in the 3rd shell to become magnesium 2+ than it is to fill 1, 2, 3, 4, 5, 6 more electrons in the 3rd shell to satisfy the octet. So when magnesium loses 2 electrons, we become magnesium 2+. Now, nonmetals in groups 5A, 6A, and 7A. So these 3 groups right here. Again, we are focusing on the nonmetals, so everything above the zigzag have high ionization energies. So they will readily gain 1 or more valence electrons to form ions with the negative charges. And again, they are going to gain electrons until they have the same number of valence electrons as their nearest noble gas to satisfy their octet. And typically they're named using the first syllable of its element name followed by "ide." So if we were looking at oxygen, oxygen is a group 5A element. It's going to pick up 1, 2 electrons to become like neon. So we would write it as O2-, or the oxide ion. So again, we can look at that through the example of chloride. Chloride, if you notice, is right here in the 7A block, meaning it has 7 valence electrons. So we can count that: 1, 2, 3, 4, 5, 6, 7. It's going to be much easier for chloride to gain a valence electron, becoming chloride 1- than it is for chloride to lose 1, 2, 3, 4, 5, 6, 7 electrons and drop down in energy level. And because chloride and all of these elements that we're talking about in this part of the periodic table have very high ionization energies, they're greedy for electrons. They love picking up electrons. So gaining electrons to satisfy the octet here is much easier for these nonmetals than it is for the metals we were talking about in the other cation examples. Again, we can also look at oxygen. If you recall from the periodic table, oxygen is a group 5A element. So it has 5 valence electrons in its shell. 1, 2, 3, 4. Oh, I'm sorry. I can read. It is a 6A. That writing is very small. 6A element, meaning it has 6 valence electrons. 1, 2, 3, 4, 5, 6 electrons in its valence shell. Again, it is going to have a stronger desire to satisfy the octet by picking up 2 electrons to become like its nearest noble gas. And so we will end up with the oxide ion with O2-. Again, we can easily use the periodic table to help us predict the charges on these cations. Again, if you are talking about our metals, specifically the group 1A, 2A, 3A, 4A metals, they are going to prefer to lose electrons to become positively charged. So you're going to end up with a 1 plus, 2 plus, 3 plus, or 4 plus. Again, we're talking about these are for the metals, right? So anything here in blue. Whereas our nonmetals are going to gain electrons in order to become like their nearest noble gas. And so we can count over to see how many electrons we would gain, right? So if we're talking about nitrogen, we would count towards the noble gas, 1, 2, 3. So nitrogen would like to pick up 3 electrons. Oxygen, 1, 2, would like to pick up 2. Okay? If it helps you guys, you can write this on your periodic table that I have handed out to you up top. And so maybe that will help you remember what charges different elements will take on if it is to become an ion. Again, just remember that when we're looking at our metal versus non-metal differentiation, the metals are going to be the cations, right? So here, when we're talking about is it 4 plus or 4 minus, the 4 pluses are going to exist down here. The 4 minuses are going to exist up here. Our transition metals don't relatively ionize. Don't really look at those often as ions. It's really going to be only occurring between a metal and a non-metal. Now, these guys right here, these are our transition metals, and they're a little bit trickier because they can actually take up multiple charge states, and we're going to talk about that. But first off, let's talk about why ions are important. So there are a number of medically important ions. For one, sodium ions regulate osmotic pressure and the body's water content. They help transmit nerve signals as well as help with muscle contraction. Potassium ions will also help with nerve signaling and muscle contraction, especially in the heart. Magnesium cations are really important, again, in muscle contraction, but they're also important in bone and teeth formation and are often seen in physiological enzymatic reactions in the body. They're often a cofactor that is needed for reactions to occur. Calcium is also important in nerve signaling and muscle contraction, as well as in helping with bone and teeth formation. But it also helps in blood clotting. And then chloride, sort of like sodium, helps regulate osmotic pressure and the body's water content, as well as it's important in helping with digestion through the secretion of stomach acid and other channels. So chloride is often an ion that's used to help open up channels and cell membranes for the delivery of different things. So our first guided practice, write and name the symbol of an ion with 16 protons and 18 electrons. So the first thing you would want to do when you're approached with a question like this is always turn to your periodic table. So remember, if we're talking about 16 protons, remember the number of protons is the identifying property of any element. So you want to find which element has the atomic number 16. Then identify that, okay, we have 2 more electrons than we do protons, so it's going to be negatively charged, and it's going to be a 2 minus. So if you turn to your periodic table, you should have seen that the element with the atomic number 16 is sulfur. So the symbol for that is going to be an S. An ion of sulfur with 18 electrons gives sulfur a charge of 2 minus, so we would then write the symbol as S2 minus. Since it is an anion, we are going to use the name, or we're going to name it using the first syllable of the element name followed by "ide." So we would write this as sulfide. All right. Our next guided practice, let's predict the charge and the name of the ion of Sr. So again, you're going to go to the periodic table. You're going to find the element Sr and identify first, is it a metal or non-metal? If it's a metal, we are going to lose electrons to become like our nearest noble gas. If it is a non-metal, we're going to gain electrons to become like our nearest noble gas. All right, so hopefully you went to the periodic table and you found that strontium is a 2A group element, making it a metal. Therefore, it is more likely to lose those 2 electrons to satisfy its octet, becoming a 2+ cation. Therefore, the formula would be written as Sr2+. Because it is a cation, the name of the ion is the same as the name of the element. So we would write the name as strontium. So remember, anions or negative charged atoms will become the first half of the name followed by "ide," where the cation's name stays the same as the element's name. All right, so now it's your turn. Log in to Mastering Chemistry 4 and open the assignment Chapter 4, Ionic and Molecular Compounds in class. I have removed the password for this one, so you don't have to get the password. And then complete questions 1 through 2, and feel free to work with a partner. Pause here, and when you're ready to come back, resume the video. All right, so now that we've sort of identified ions and identified what kind of charges different ions will take on based on their location on the periodic table, now let's talk about how we form ionic compounds. So ionic compounds consist of positive and negative ions. They have attractions called ionic bonds between the positively and negatively charged ions. They typically have very high melting points and are often solids at room temperature. So our sort of most famous example of an ionic compound is table salt, sodium chloride. In the chemical formula, the symbols and subscripts of ions are written in the lowest whole number ratio of the atoms or ions. The sum of ionic charges in the formula must equal 0. Therefore, when we're creating our ratios of our 2 ions, our cation and our anion, we want to balance the number of atoms in the formula such that we get an overall 0 charge on our molecule. So the total positive charge must equal the total negative charge. So for example, sodium is likely to lose an electron to become 1+. Chloride can then take that electron from sodium because chloride wants to gain 1 electron to become chloride 1-. Remember, we already identified that when we identified the charge states that different elements like to take on based on their location on the periodic table or their number of valence electrons. So if sodium is a 1+ and chloride is a 1-, then if we have a 1-to-1 ratio, 1 sodium, 1 chloride, 1+ charge, 1- charge, a 1 times 1 plus 1 times -1 gives us 0. Therefore, our ratio of sodium to chloride atoms in our ionic compound will be 1-to-1. Now, magnesium, on the other hand, is a group 2A element, so it's going to give up 2 electrons. When it does that, it's going to need 2 chloride atoms now because chlorides only want 1 electron each. So magnesium will give up 1 electron to 1 chloride and a 2nd electron to the other chloride. We will end up with magnesium 2+ and then 2 chloride 1- ions, right? So again, mathematically, we can look at this as here's magnesium 2+, And here's our 2 chloride atoms, right? We have 1 times 2 plus to give us 2, plus the 2 chloride anions times 1 minus will give us -2. So 2 minus 2 equals 0. So our molecular formula then for magnesium chloride will be MgCl2. The subscript down here is going to tell us that we have 2 chloride atoms or ions in our ionic compound. So to balance the ionic charge in an ionic compound, again, the goal is such that the total positive charge is going to equal the total negative charge. So again, one more example, if we're talking about sodium sulfide, right? If we look at sulfur on the periodic table, we'll see that sulfur has 6 valence electrons, so it needs 2 electrons, and so sulfur is going to have a 2- charge on its ion. However, sodium, again, is a group 1A metal, so it's going to be sodium 1+. So in order to balance out the 2- charge on sulfide, we need 2 sodium ions with their 1+ charges. So 2 times 1+ plus 1 times 2- gives us 0. So 2 sodiums and 1 sulfur. All right, so let's practice this. Here we're asked to write the ionic formula of the compound with the common ions of barium and chlorine. So the first thing you want to do is identify the charge state for each ion using the rules from the previous section and write the formula for each ion. So if you go to the periodic table, you should find that barium is a 2A group element. Therefore, it will lose 2 electrons to become barium 2+. Chlorine is an 7A group element. Therefore, it will gain 1 electron to become chloride 1-. So we can write that down, barium 2+ and chloride 1-. Our second step then is to balance the charges, or the number outside of the parentheses, in order to figure out what ratio of barium and chloride do we need in order to get a net 0 charge. So the charges go inside our parentheses, right? So the 2+ for barium and the 1- for chloride go inside the parentheses. What goes outside the parentheses is whatever numbers we need in order to balance these charges and give us a 0. So if we have a 2+ on the inside here and a 1- on the inside, we need 1 out here, right? 1 times 2+ gives us 2. And then ask ourselves, okay, what times -1 would also give us 2? Well, it needs to be 2. So 1 times 2 plus 2 times -1 gives us 0. The number that we write on the outside of these parentheses in order to become neutral is going to be the subscript in our ionic formula. So to write our ionic formula, we will write the cation first, our metal first, and the anion second, and then we'll insert our subscripts. So because barium would have a subscript of 1, right? Our 1 is the outside of the parentheses. Then we don't include it because we assume if there's no number here, we assume it is 1. However, chloride should have a subscript of 2 because we need 2 chloride ions to balance out the 1 barium. So we would write Cl2. Now, when we are naming ionic compounds, the name of the metal is written first and is the same as the name of the element. So, for example, when we're talking about NaCl, we would write sodium because the cation's name is going to be the same as the element's name. Then we would write the name of the nonmetal. Then we write the name of the nonmetal. And when we write it, it's the first syllable of the nonmetal name plus "ide," and it is written second, right? So for NaCl, that would be the Cl becomes chlor, right? The first syllable, "ide," right? Ending in "ide." So all together, it will be sodium chloride. And we do have a space between the name of the metal and the nonmetal. All right, so let's practice this by writing the ionic compound K2O. So step 1, identify the cation and anion. So the cation is K+. It is from the group 1A elements, and the anion is O2-, which is the group 6A elements. Step 2, name the cation by its element name. So since the cation is K+, we just name it potassium. Step 3, name the anion using the first syllable of its element name followed by "ide." The name of this anion is then oxide. Step 4, write the name of the cation first and the name of the anion second. So it will be potassium oxide. Now note, there are 2 potassiums here. We're not writing anything to indicate how many potassiums are in the name. We will do that when we start talking about molecular compounds, but for ionic compounds, we do not have to signify how many atoms or ions are present in the formula, because we can figure that out by looking at the valence electrons and predicting the charge on the ions, right? If we know the charge of the ions for each element in the formula, then we can predict the ratios. We don't have to disclose that in the name. All right, so your turn. Working with a partner, write the formulas and names for the compounds of the following ions. All right, so pause here and see if you can figure this out on your own. If you have questions, feel free to reach out. All right, let's talk about working with transition metals. So let's go back a little bit. Close your eyes if this bothers you. But remember when we were talking about how we can predict the charges of certain elements or certain ions by just looking at the periodic table? Well, that's really easy for the edges of the table. But the middle of the table, this group of elements here, these are our transition metals. And if you remember, these are where we sort of introduce the d orbitals that can come into play. And because of these d orbitals, we can get some fun chemistry going on. And what that means is that a lot of the elements here in this section of the table can take up multiple charges on the periodic table. All right, so now that we've reoriented ourselves with which elements we're talking about, let's talk about that. Oops, I went too far. Okay, so transition metals, except for a few, zinc, cadmium, and silver, all the other ones can take on 2 or more different positive ions. So they can have multiple charge states. Typically, we use a Roman numeral that is equal to the ion charge in parentheses after the metal's name in order to help signify which cation is going to be used in the formula. So for example, chromium, we can have chromium 2 or chromium 3 to signify the 2+ or 3+ cations. Same thing with mercury. We can have mercury 1 or mercury 2, tin, mercury 2, tin 2 or tin 4, and also iron 2 or iron 3, right? These are all just different examples of these transition state metals. So how do we determine the transition metal charge state? Using the charge on the anion and the charge balance, we can actually predict which cation of a transition metal we are using. So for example, if we're talking about manganese fluoride, if we're looking at the chemical formula, MnF2, well, we know that fluoride is only going to have one charge state. Fluoride being a group 7A element only needs one electron to satisfy its octet. So it's going to be a 1- charge right here. If there's 2 of them and only one manganese, well, that means that manganese must have a 2+ charge on it to balance out the 2 1- charges on fluorines. So therefore, we would write the name of this ionic compound as manganese Roman numeral 2 to indicate that 2+ charge on that one manganese ion, fluoride. So manganese 2 fluoride. All right, so let's practice this. Name the ionic compound iron chloride, right? So with iron and chloride. So the first thing you want to do, again, is identify the charge of the transition metal cation by looking at the counter element in the formula. In this case, the ion of chloride. Again, since chloride is a group 7A element, it is likely to only gain an electron to have a 1- charge, so it would be chloride 1-. Since the molecular formula has 2 chlorides, that gives us a total of 2 times 1- or a 2- charge from the chloride anions. To balance their charges with only one iron atom, the iron must have a 2+ charge state. Therefore, we would then write the name of the cation by its element name and then use the Roman numeral to represent the charge. So if it's a 2+, we would say it's iron with the Roman numeral 2, or iron 2. In step 3, we would name the anion, again using the first syllable of its element name followed by "ide," chloride, and then we would put it all together. So iron 2 chloride. Again, we were predicting the charge state of the transition metal by looking at its anion partner in the molecular formula. Okay? So now we can also go the other way. So write the formula for if given the name of the ionic compound using a transition metal. So here we are told we have iron 3 chloride. So the first thing we want to do is identify the cation and the anion. So we're given now the charge state of our transition metal, so we know it's a 3+ version of iron, and chloride we know is going to be a 1-. To balance the charges then, we have to write our charges inside the parentheses, and then outside the parentheses will become our subscripts in our formula. So we have to predict what ratio of iron and chloride is needed to give us a net zero charge. In this case, if we had one iron atom, that would be a 3+ charge. To balance out that 3+ charge with the chloride's 1-, we would need 3 of those atoms. A nice easy way to do this, guys, is to do what's called the crisscross. So you take the charge of the cation and crisscross it to go under the anion. So the 3 would come here, and you take the charge of the anion and crisscross it to the cation, so it becomes the subscript. So we would put a 3 here and a 1 there. We'd end up with iron, 1 iron atom and 3 chloride atoms. So either way, if you like to use the mathematical approach by sort of plugging in numbers to find where we can get 0, or the crisscross method, either one works. All right, your turn. So go ahead and go back to chapter 4 on mastering chemistry. And now let's answer questions 3 through 5 on naming and identifying the charge states of different transition metals in ionic formulas. All right, pause, and then when you're ready, come back. All right, finally, sometimes we have charges on things that are not just a single atom or element. Sometimes we have what's called polyatomic ions, and polyatomic ions are charged species that consist of 2 or more atoms covalently bonded together. So this table sort of gives you the most common. Ammonium, which is NH4, has a 1+ charge. Another popular one that we may run across a lot is nitrate or nitrite, phosphate, sulfate, perchlorate, right? These are all, and then hydroxide, that's another really common one that we may run across as we work examples on homework or the tests. You will not have to memorize these. I will let you know what the charge state is of the polyatomic ion, but what you need to remember is when we are working with polyatomic ions, you have to work with them as one whole unit. You can't break apart the atoms of the polyatomic ion. So basically, we often will hide these under a parentheses within the name of it so that you know that it is like a unit, right? You can't just break it apart. So again, polyatomic ions are a group of covalently bonded atoms with an overall ionic charge. They often consist of a nonmetal such as phosphorus, sulfur, carbon, or nitrogen that are covalently bonded to other oxygen atoms. They usually have a 1-, 2-, or 3- charge. Most of them are negative except for ammonium, which has a positive charge. And again, you won't need to memorize these. So when writing formulas containing polyatomic ions, we use the same rules of charge balance as those for simple ionic compounds. So for example, if we're talking about magnesium nitrate, remember magnesium is a group 2A element, so it will have a 2+ charge. Nitrate, you would be given the charge for that one, and so you would see that it is a 1- charge. If we are going to create an ionic compound between these 2 ions, then we would need to balance out magnesium's 2+ charge with 2 nitrate ions. When we write the formula, the ionic formula for this compound, we would write it as magnesium, Mg, and then the nitrate gets treated as 1 unit. So we use parentheses, NO subscript 3, and then parentheses 2. So this means we have 2 of these nitrate units. So the 2 gets distributed across all of the atoms inside the parentheses, okay? And we're treating that as like 1 unit. Now, a tool that I gave y'all, or will give you guys, is this flow chart for naming chemical compounds. So this is a chart you'll be able to use on your test. And again, it just kind of helps you memorize the rules in naming ionic compounds. And we will also use rules for naming molecular compounds the next time we meet for lecture. So again, just to reiterate, ionic compounds are when you have a metal and a nonmetal. In naming, we name the metal first. Remember, metals will form only positive ions. So if there's only 1 positive ion that can be formed, then we use the name of the element or the ammonium. Again, if it's a polyatomic ion, we would say ammonium. If it's a transition state metal, meaning it can form more than one positive ion, then we use the name of the element followed by the Roman numeral that is equal to the charge. Secondly, the nonmetal, if it is a monoatomic ion or just an element ion on the periodic table, we use the first syllable of the name followed by "ide." If it's a polyatomic anion, then we just use the name of the polyatomic ion. All right, when we meet again, we'll talk about molecular compounds. All right, so that's all I have for this part of the lecture. Come back for part 2, where we will talk about molecular compounds and naming them. All right, thank you guys, and I hope you have a great day.